Very good morning to all. I'm sorry, I started without opening my mic. I'm sorry. Today we have one another very important topic which is related with metrology aspects of 5G test solutions. This is very important because in this 5G spectrum, we not only need a very good communication system, optical fibers are available all over India today through the ground and the satellite system, but also very important and accurate time dissemination. We are working on this time dissemination project under the legal metrology. We have with us Professor Kamlesh Patel, who is in the Department of Electronic Science, University of Delhi. He did his MSc in electronics, MTech in microwave electronics from University of Delhi, and PhD from DTU. He worked as a scientist in National Physical Laboratory, Delhi. He is basically involved in developing new waveguide transfer standards, enhancing the calibration range, successful international peer review, intercomparisons, measure maintenance of quality control documents, calibration activities, etc. He is an assessor for RF parameters as per 17025 ISO 2017 for NABL under the DST. Now it is under the DPIIT. He joined this University of Delhi as a professor. Now he's a professor. He was involved in establishing in new simulation and measurement facilities in the department using signal source, spectrum analyzer, etc. He is also involved in IEEE Delhi chapter. He is a member and he has done a lot of research and development work, a lot of research papers he has written. He is also involved, his research interests are involved in 5G mobile communication, MIMO antennas, electromagnetic characterization, and RF metrology. Thank you very much, sir, for accepting our request on this short duration and to enlighten us with your vast knowledge and experience to our participants. Thank you very much, sir. We have with us our Honorable Shri B.N. Dikshit, sir. Sir, would you like to speak two words, please?
Yes, Astoji.
Please, sir. Thank you very much, sir. Thank you for joining us. Thank you.
So, very good morning, Sri Astoji, Director Legal Metrology, Mr. Patel, the today's chief guest of the programs. The today topic is very important and very new topic, and this is related with the 5G, and 5G is now implemented by various telecom companies, and Department of Consumer Affairs has started a project that is called the time disseminations. This project is implemented with the help of the NPL National Physical Laboratory, ISRO, and BIPM is also one of the body by which we are getting the traceability of the systems, in which the various telecom companies, electrical companies, electronic companies, and various other companies which are related with the time disseminations, working on the time work, and their technology is working. So they are working on these very things. So it is very important that Department of Consumer Affairs is working on this very time dissemination project and providing benefit to the many industries, and that covers the telecom companies also. In that very work, it is very important that the 5G program which has been implemented, so that is certainly also with related with the time disseminations. They will get the benefit from our department and RSL, where the time dissemination project has been established, and this program will enlighten lot of things, and the benefit by which they will be get benefited from our RSL Regional Reference Standard Laboratory situated at Bangalore, Faridabad, Ahmedabad, Guwahati, and Bhubaneswar. With this very word, I wish for the success of the programs and so that the participants will be get much benefited and they will be enlightened with the new technology. Thank you, Astoji. Thank you, Patel Sahab. Thank you, all the members.
Okay.
Thank you much, sir, for your kind and motivating words. Thank you, sir. Thank you very much. Now, I would like to request Professor Kamlesh Patel to kindly enlighten us with his vast knowledge and experience. Over to you, sir. Please.
Thank you. Thank you very much. I would like to thank Mr. B. N. Dixit, former director legal metrology, for elaborating the activities of the legal metrology department. I also like to thank Dr. Ashutosh Agrawal, director legal metrology, for inviting me and organizing this wonderful various talks on the metrology under the national workshop or seminar. So today's topic is metrology aspects of 5G test solutions. And now we know that the 5G is in the boom, and most of the telecom companies are providing the mobile services with the help of 5G technology. Start with the topic. This is the location of my department, and we are situated in Delhi, Dholakuma. And here you can see the location for my department is it's known as the Department of Electronic Science, and the department was established in 1985. It was started with the MTech course in microelectronics in 1980, followed by the MSc in electronics in 1985. We are having the 40 seats and 33 seats for these two programs. Along with this, we are also running a PhD program in various fields of the electronics. So today we are going to learn, or we will have a brief introduction about the 5G technology. We will also see the features or the specification comparison of the 1G to the 5G network. Then we will come to the 5G key features, applications of the 5G networks, and what will be the typical measurement setup for the 5G measurement or the 5G devices measurement. And then we will elaborate how the different NMIs in all over the world have worked for the metrology for 5G communications. There are some important communication terms which need to define. So we will define the signal to noise ratio, bit error rate, EVM, and the SINR. So SINR will be the new or important topic, which is very much in demand for the metrology aspects. So we will see what is the status of different NMIs, what they have developed the different measurement techniques to measure the SNIR parameter for the metrology in 5G network. And then we will just conclude our talk with the future work in the 5G metrology. So starting with the evolution of the mobile communication generation, which is starting from the 1G to 5G. Now most of the people are working in the research level for the 6G technology. So we have moved from the communication through the analog device to the new kind of a form of communication. Like in addition to the voice and video communication, we can able to transfer now the now many document or various kind of high gigabits of films, or you can say the video files through the wide internet services. At the same time, we need to communicate with more and more number of people, because the world population as well as the mobile devices which is being used by this population, or the world population is also exponentially growth. So with the increase of the more number of devices or the electronic devices, there is a requirement of faster speed. And you can see here that we have moved from the 21.1 megabits per second in 3G network to the 10 gigabits per second in a 5G network. So there are some technologies which are being enhanced or implemented with the time. We can also compare the features of the 1G and 1G to the 5G and 6G, where the 5G is based on the multiple in multiple output system and the millimeter wave techniques, while in the coming 6G, the new kind of a radio access network will be implemented in the terahertz frequency. So the operating frequency range will be different for these two bands, 5G generation and the 6G generation. So when we talk about the SS system, the OFDM or the BDM technique will be used, and all the communications will be based on or rely on the internet. So there are some detail of the term which is being used in the 5G and 6G network. Services of the 5G network with the higher advanced communication system, we will able to collect more number of data, more number of communications, as well as the connectivity of the devices will be more. So in every way, we need to have our speed faster, because we are looking that our information or our message should be reached to other end as soon as possible. So the enhanced mobile broadband technique technology is developed, which delivers the high quality internet access even in a very harsh condition. So whenever you go inside any ground level or you reach to any top of the mountain, there is a limited bandwidth or limited signal. So that problem will be removed with the help of this enhanced mobile broadband, as well as there will be faster communication. Okay, so our government has already started talking about like bullet train implementation. So bullet train speed is almost 300 kilometer per hour, and at that situation, if anybody want to communicate with a person who is out of the train or situated at other place, our mobile signals should able to reach to a faster moving train or the bullet train without any interruption. So for that, the signal should reach as smooth as fast as it can be. So the technology is developed that is known as the ultra reliable low latency communication, which actually reduces the communication between the two mobile devices is less than 4 milliseconds. That means within a 4 millisecond, the signal will reach to one end to the other end of the mobile device. Okay, the next is the massive machine communication system. We are expecting that in the coming days, the vehicle will start communicating, and we are talking about like driverless automobile system. Okay, so there will be some vehicles which are not require any driver. So the system, the car or the vehicle should have the small kind of electronic devices which can able to communicate about the traffic condition on the road, or the health status of the driver or the passenger. So for these, there are multiple devices which should able to communicate with each other. So we are talking about the massive device connectivity for the Internet of a Thing applications. So that technique is also developed and implemented in a 5G. So that is the 5G massive machine communication system. So these three are the main technology which is being developed and supporting the services of 5G. Talking about the 5G frequency range, there are two frequency band, FR1 and FR2, which is covering the range for the 5G. The lower 5G communication, that is FR1, starting from the 410 megahertz to 7.125 gigahertz, that is meant for the mobile communication. The second one is FR2, 24 gigahertz to 52 gigahertz, that is meant, or that is that will be used for the health monitoring of the patient, as well as some radar and satellite applications. So while we talk about that for the lower frequency band, that is FR1, the mobile tower will be placed having a little bit large area of the cell, while in case of the millimeter wave, which is covering from 24 to 52 gigahertz of frequencies, the cell size will be very small. So in a small area, more number of cells will be required to have a proper communications. So these frequency bands are decided by the third generation partnership project under the and along with the ITU. That is, ITU stands for the International Telecommunication Union. So in the coming days, we will also have the implementation of the 6G technology, which will be covering the 7.125 to 24.25 gigahertz. So all the mobile tower which we are going to discuss in coming slides will be carrying the operating frequency range either in a FR1 or FR2. Simple mobile tower is containing the two main unit. One is the radio remote unit. The second one is the baseband unit. So here is the radio remote unit, which actually talking about or communicating in microwave frequency range, whereas the baseband unit is actually the signal which is demodulated, the signal or the small frequency signal, and it is actually sending the frequency to the RRU. So if this is UE, that is the user equipment or kind of a mobile, is giving some signal to the mobile tower. The mobile tower is sending some signal, the same signal in a downlink form. So there is a slight frequency deviation between the uplink and downlink frequency. So this is mainly containing the two units. One is the radio remote unit, and the second one is the baseband unit. Now, with the enhancement or the advancement of the mobile technology, thus the component or the devices which is being used in a mobile tower is also gradually changed. So when we talk about the traditional 1G and 2G, which consists of the baseband unit and the radio head together, and the antennas are connected through the amplifier and the coaxial cable. Okay, so they are kind of a lossy devices, and amplifier as well as the coaxial are offering the additional loss, or you can say the noise in the baseband signal. So to reduce this kind of a signal, the optical fiber is connected for the 3G and 4G communication. Although there is a addition of the, or you can say the maintenance of the coaxial is required between the remote radio heads and the antennas. In the next 4.G and the 5G technology, that is also removed, and we are using, or the mobile companies are using the virtual baseband cloud, and the antennas are directly connected with a fiber front hole. So this is the advantage, that all of the losses which is occurring earlier in a coaxial cable or the noise generated by the amplifier, all are removed in the new technology under the 5G. Also, the size of the antenna is also changed. So we are using the more number of antennas in the 5G technology. Okay, so one more thing, that the mobile technologies are also using advanced modulation technique. The new modulation technique, which is known as the quadrature amplitude modulation, and the quadrature amplitude modulation is talking about the two different kind of a modulation. Like this is a digital signal which is given by 0101 or 0010100111. So this is one signal, and this one is another signal 0011. So 00 is representing the low level of the signal, 11 is representing the high level of a signal. So these two are the baseband signal or the information signal, which has to be transmitted over a carrier frequency. So this black is representing the carrier frequency. Carrier frequency may be same, but depending on the input baseband signal, the modulated signal will be different. So we are having the one modulated signal here. We are having the another modulated signal on this side. So one is changing the amplitude of the modulated signal as per the baseband signal 1, and this is the baseband signal 2. So we are having the two modulated signal, and these two modulated signal can be simultaneously transferred, and that's why we are having the quadrature amplitude modulation. So amplitude of the signal is controlled by the two signals, as well as the position of the two signals are such that both are having the 90-degree of phase difference. Okay, with addition of this one. So that's why we are having the two signals which are having a phase difference of quadrature. So gradually, this is the example of a two signals. We can add more and more number of signal, and from there we can obtain 64 QAM signal and 256 QAM signal, depending on the value of the number of signals being used. One more multiplexing, that is known as the orthogonal frequency division multiplexing. That means you can able to send the different value of frequencies or different information at different frequencies. So for this, the first signal is done as a QM signal, like we have explained one example of a QM signal generation. So once the QM signal is generated under the frequency domain, after following a IFFT inverse Fourier transform at a transmitter end, it is sent to the free space. On the receiver side, it is down converted or reverse converted from the FFT fast Fourier technique, and then it is jumping back to the frequency domain QAM signal. So this is one of the method how the OFD being implemented. So this all process is done at a baseband unit of the mobile tower. On the tower side, since we wanted to increase the channel capacity of the signal, so this is a small formula, m and b log base to 1 plus Sn, and the value of Sn is actually controlling the value of channel capacity. Since the value of number of antennas on the receiver side as well as on the transmitter side can be fixed, we can able to control the value of channel capacity only with the help of Sn S by n. So if you want to increase high value of channel capacity, just increase the value of S by n, which is again a very costly affair. So this is the demonstration of the MIMO system. MIMO system, multiple in, multiple out. We can have the more number of antennas on the transmitter side, same on the receiver side. So more number of antennas being communicated together, we can have the large amount of the channel capacity. There are some advantages of the MIMO system, like we can increase the data rate, signal quality can be increased, we can also enhance the spectral efficiency, and also they are compatible with the existing standards of the 4 and 3G. So all these benefits are being utilized in 5G new radio, and for the realization of the 5G new radio, we have to have one OFDM based waveform. This is another example of the OFDM based OFDM waveform. So we can have the different channels in a certain frequency range, channel 1 to let's say channel 10. If you are able to accommodate remaining channels in between, like there is a gap between the each band, small band, so we can transmit another channel here. So this is a transmission of or the rearrangement of the channels, or you can say multi-carrier techniques, that in the gap of channel 1 and channel 3 we can able to place the channel 2. Okay, similarly between channel 3 and channel 5 we can place one channel 4. So this is in comparison to the conventional multi-carrier techniques, the orthogonal multi-carrier techniques are giving advantages of saving of bandwidth. So you can see here with this with this technique, 50% of bandwidth can be saved, and we can able to transmit another amount of a channel. So ultimately, by arranging the orthogonal multi-carrier technique, we can able to add double number of mobile channels for the communication purpose. So that is the advantage of the 5G NR, that it can able to offer you more number of channels in a small span of the frequency. 5G also employs the massive MIMO. Massive MIMO means we are having the two antenna on the like a transmitter, two antenna like a receiver. We can also make that 4x4. Four antenna can be acted as a transmitter and receiver. We can increase more number of antennas, and that will lead to the term massive MIMO. Okay, multiple and multiple output, there will be more number. So we can have the 32, we can have the 64 number of antennas placed in a mobile tower. Okay, another term is the beam forming. So the normal antenna which does not have any beam forming is giving you the same amount of the or is radiating the same amount of power irrespective of the number of devices, and it is having some limited area. Okay, so what happens, the amount of power which is being transmitted from the legacy antenna is actually distributed among the number of users, as well as the signal is being offsetted by the buildings or any kind of a system. So to remove this, 3D beam forming is proposed, that with respect to time or with respect to frequency, we can able to transmit some amount of a signal directly with a high value of amplitude to a certain direction. So we can able to control the amount and direction of a beam to send in a certain direction. So this is a representation of the 3D beam forming, which is suggesting the two different color. These two different colors is suggesting, since there is a building which reduces the amount of signal strength, since there is an attenuation of a signal or transmitted signal due to the building. So the user which is sitting or which is inside this building must receive the high amount of a signal from the mobile tower. Okay, so here we need to increase the value of a signal strength. While in this case, since this is in the open air, the signal strength does not require much strength. So we can able to distinguish the amount of signal strength required depending on the situation or the location of the user. So that is the advantage of the 3D beam forming, which is again being implemented in the 5G NR. The third one is the use of the millimeter wave frequencies. That means 100 gigahertz signal we can use, but for this is for some other applications. So there are two different wave bands. One is frequency below the 6 gigahertz, and the other is higher than 100 gigahertz. So there are good opportunities which is offered by the 5G system or the 5G technology, that it is offering you the high value of a bandwidth. So higher bandwidth, that means high data rate we can have. Beamforming technique, I have shown you this example. Multi-connectivity, more number of devices will be connected, so that requires a demand of the higher data rate. And there will be the new use cases, like I also mentioned, that communication between the vehicles or the vehicle to vehicle communication. So that will be the new era which will lead to the driverless cars. Okay, so there are some challenges for the measurement expert, that if the distance at millimeter wave is reduced, how one can able to increase or how can able to have the reliable measurement. So also for the high frequency generation or the communication for a very high frequency, more than 24 gigahertz, the design as well as the device design become more complex. When we talk about the beamforming requires more number of antennas to be placed in a mobile tower, and that also leads to give a new set of the measurement for more number of antenna testing. And one of the important testing which is preferred is the over the air, that's OTA. And also the system should exist with another system. So right now, which mobile phones which we are having today is having the more number of a communication system. It is also supporting the GSM. It is also supporting the 3G, 4G as well as the 5G. So the mobile itself is having a device which is able to communicate with different generations. So the coexistence of these generations should be maintained while implementing the 5G technology. And then there is a requirement for a cyber security and some test for the 5G. So we rely our all measurement, or we will rely only on the measurement for this testing the product or any new product development. So there are development in the metrology in various fields for the society application, energy, health, environment, industry, new technology, as well as the most of the NMIs are working on the future measurement standard, which will lead to the standardization of the new kind of a measurement method and the parameter. So a typical 5G setup will involve a function generator, a signal generator, and a power sensor. So the signal generator will generate a various kind of a frequency and as well as the different modulation. So for the downlink and the uplink, we can have a different modulation techniques. For example, downlink technique, we are having the CP/OFDM, that is the cyclic prefix orthogonal frequency division multiplexing. And for the uplink, the different modulation technique is used. Since the frequency of these two are different, they may able to create the interference between these two. So the different modulation techniques are applied. So any signal which is being received from the mobile tower to mobile is having the multiplexing technique CP/OFDM. The signal which is being transmitted from the mobile to the mobile tower is having the multiplexing technique DFTS/OFDM. So frequency of the downlink and uplink signals may be same, but the modulation involved in these two signals are different. So it can be distinguished. This is the power sensor. The power sensor actually receives the power from the signal generator, and this is having a capability in the range like say 50 megahertz to 6 gigahertz. It can able to measure the power from minus 130 dBm to plus 20 dBm, and with a measurement bandwidth of 100 megahertz with IQ data capturing. So this is a small setup for any 5G signal. And again, the power sensor is connected to a software. The software will give you different value of data. Like it can also it can giving you the 5G NR1, that is the amount of a signal with respect to time. What is the constellation diagram? That means with respect to the phase, how the signal is being changed. It is also giving very important parameter, that is error vector magnitude of different modulation signals. So I only discuss about the QAM signal, but there are some other quadrature PSK modulation signal, and these signals are being also characterized. So this small setup is sufficient to give you information about the signals being generated and their properties at 5G range. Okay, so why we are looking for the metrology for 5G test solutions? So there are some important thing which has to be fulfilled for the 5G system. The first thing is that metrology for 5G system is actually catering the 5G signals, the devices, antennas, and the systems which are operating at 5G frequency bands. So it is important that whatever be the company which are operating or which are developing product for the 5G technology must meet performance meeting to the metrology requirement, as well as these 5G new product should be sufficiently safe for the people as well as the environment. So this is two important thing which has to be offered to the companies which are producing the 5G product, that we are having a proper measurement system. All the components should have a safe and reliable range of limit, so it can able to it does not harm any people or any our natural environment. So we are looking for importance of the microwave or sorry, metrology for the 5G system. So this will ensure the performance requirements, safety of a people and environment, as well as once we are able to establish a proper metrology for 5G, it will also help us to establish or looking for a new technology which will cater the 6G networks and the product. So what is the metrology for the 5G system? So this includes measuring signal devices, antenna and systems. It is also measuring the radio frequency exposure. Very less people talk about the radio frequency exposure to the human, plants as well as animals. So 5G systems are talking is working in different frequency range. So we need to have a sufficient number of data about to check about the radio frequency exposure. So this is also a part of the metrology for the 5G systems. We need to develop methods to evaluate the wireless system performance, and that's why there is a new parameter is introduced that is known as the signal to interference plus noise ratio. So most of the NMIs, including the NPL UK and some European countries NMIs, as well as the NIST, they conclude to a one point that we must able to measure the SINR, and we should able to establish the traceability of this parameter with the known parameter. For this, a project was started in 2015, given by the Euromet, that's the European Association of National Metrology Institute. They have given a project under the program of European Metrology for Innovation and Research. The title of the project was Metrology for the 5G Communication, and the coordinator of this project was Tian Hong Lo from NPL UK. So they are having some thought in mind that we should able to establish the SNR measurement facility. We will define the new concept or definition for the SNIR. They will also decided to establish the SNIR measurement as well as the MIMO measurement for frequency up to 100 gigahertz, and also they are looking for the non-linear measurement, since the products developing at a 5G consisting of the active as well as the passive devices. So it was planned that these all measurement or the project should be complete within the 3 years, so that the 5G network can be deployed from 2020 year 2020. So there are three Euromet NMIs which participated. One is the CMI from the Asia, NPL UK, and the RISE Sweden. Okay. Along with that, they also partnered with the industry and the academia. So from the academia, the University of Surrey from United Kingdom was part of this project, and the NSU, Chalmers, and Keysight Technology. These are the companies which also the participant in this project. So there are total 7 members, 3 NMIs and 3 this academic and industry partner, which collaborated for the metrology for 5G communication. So the purpose of the metrology project that they should develop a proper measurement method and the guidelines for the network operator, digital industries, for device developers, as well as they should be able to look for a new test methods, as the two objectives have to be addressed. The new parameter, that is SINR, should be properly defined and measured. The second, the measurement should be done in a MIMO system. Okay, so we come to the they decided to make the 4 objectives. One is to define and develop traceable methods to measure signal to interference plus noise ratio over a wide frequency range. Second, to develop metrology for the traceable MIMO antenna system, since the MIMO is containing the more number of antennas on the transmitter and the receiver. So there is a various aspects which may able to interfere the signal of the which can interfere the transmitted signal. Third, to develop traceable metrology for the 5G mobile communication devices. So there are traceability metrology already established for measurement of a power, for measurement of the various network parameter like X parameter and the S parameter. So they wanted to evaluate the value of SNIR with the help of these parameter, and then trying to establish a good traceability between the SINR and the existing parameter. Finally, they also wanted to engage the industry, so the product developed by the industry is compatible with the 5G metrology. So the Keysight technology has developed a modulation distortion software which can able to implement it in their product named PNAX Vector Network Analyzer, and this particular software is having having some uncertainty contribution for establishing the traceability with the SNIR and the other related terms. So before jumping to the SINR measurement, let's define what are the important parameter which is known by the metrology group. So one important parameter which is actually is the ratio or the power of a signal to the power of the background noise, and it is actually expressed in terms of a dB. So signal to noise ratio is a important parameter which indicates the amount of a signal, which indicates the clarity of a signal with a less amount of a noise, and this actually a performance matrix for a communication system. Then the second parameter is the bit error rate, and it is a rate at which the errors occurs in a transmitted data stream, and lower bit error rate actually indicates the more reliable communication system. There is relationship between the SNR and the BER, and eventually this is inversely proportional to there's an inverse proportionality between these two. And but in the digital communication, depending on the modulation, the relationship between BER and the SNR are getting changed. So for example, the BPSK, binary phase shifting key, the BER is given by half of ERF with under root of SNR. So ERFC is the complementary error fraction. So there are certain value of the SNR for which we should not able to transfer any communication system or any signal. So that is defined by the threshold of the SNR. For example, SNR higher than 10 dB for more than 10 relay nodes with 16 QAM signal is sufficient. Okay, if the SNR is less than 10 dB, the bit error rate will be significantly high. Mathematically, the SNR is defined as a signal to power to the noise ratio, and since every signal is containing the two component, one is in phase, another is out of phase. So the we get the ratio of the signal power with IT square plus QT square, and the NIT and NQT are representing the in phase and quadrature noise amplitude of the T signals. So we can have this ratio to simply define the value of SNR. Similarly, bit error rate is defined with this equation where the parameters are given like L is the number of labels in each dimension. Okay, so we can correlate the value of bit error rate with SNR by replacing the value of EB by N naught. So we replace the EB by N naught by SNR, where this ES is given as a log base to M into EB. So M is representing M array modulation. So there are some more equations which is defining the value of error vector magnitude. So bit error rate was okay when we are able to measure the value of SNR. Now the new parameter is defined, EVM, which is a measure of errors between the measured symbol and the expected symbol. So we wanted to send some amount of the digital signal. Okay, symbol means, so this part already mentioned here. So this 00100111 is representing the symbols. So we wanted that these symbols are transmitted from the transmitter side, and how much is received on the receiver side. The difference of these two, is termed as a error vector magnitude. So the known symbols are already new on the transmitter side. That has to be compared with the measured symbol on the receiver side. Any difference is termed as a error vector magnitude. So the use of the EVM as a performance matrix is limited to the radio frequency, which shows the inter-reception, the performance of the receiver. So there is a guidelines defined by IEEE 80.211A in 1999, which defined the EVM as the root mean square value of the difference between collection of the measured symbols and the ideal symbol. So ideal symbol will be known as 0n, and any difference between the measured symbol, this difference divided by the actual ideal symbol is taken as a EVM RMS. So this is again taken care by the measurement equipment. There are some more equations defined, like normalizing scaling factor. We also define one more parameter, total power of the measured constellation of the T symbols. So these all of the technical term. I'm just skipping a little quick. So EVM RMS is having a function of the signals as well as the difference between the in phase and the quadrature phase component. So in short, we can relate the EVM as inversely proportional to SNR under root of SNR, which is N naught by ES half. Okay, and from there, if we substitute this value in the BER equation, bit error rate equation, we relate the value of bit error rate with the EVM. So there is a relationship between, or establishment of the relationship between the BER and the EVM. Next important parameter is the signal to interface plus noise ratio, which is actually defined as a 10 log base 10 signal over interface plus noise. So there is a difference between the SNR and SINR. SNR also taken care of the interference. Okay, so there is some significance of the SINR. Higher SINR values corresponds to clear, more reliable signals, leading to better overall communication performance, such as faster data speeds and more reliable connections. So there is some range for SNR values greater than 20 dB. It is assumed that the communication system performance is excellent. If the range of the SINR is between 13 to 20 dB, it is taken as a good range. Below 13 dB is taken as a moderate, and SNIR less than 0 dB signal quantity is assumed to be poor. So the parameter of the SNR value, or the parameter SNR value, define the quality of the overall communication performance. So if the value of SNR is less than 0 dB, the performance of the communication system may be significantly degraded, which will lead to the slower data speed and higher data rate. So SNR value define the quality as well as the data speed of any communication system. Okay, so Gupta and Kumar, they proposed one physical model for SNIR SJ, which is given by this formula, and there is some threshold limit is fixed, which is also written in other form, where PRSI denotes the signal power received at node at SJ from the node SI. So any signal which is not desired is taken as a noise or the interference of the signal. So there are two components of any signal. One is the noise, which is coming through the transmission, and the second one is the interference, which is coming from the other source. So while starting the metrology project, they first analyze why we need to study the new parameter, that is SINR. So there is a small but significant difference between the signal to noise ratio and the signal to interference plus noise ratio is that SNR is used as a matrix for the radio signal quality. okay, for device testing. So if you want to test any device performance, go and check the parameter SNR. But for the 5G, signal quality is more influenced by interference between the devices than the equipment noise. So in 5G, conclusion is that the 5G signals are facing interference by the communicating devices or from the different devices. A mobile device itself does not generate any amount of the interference. So to define or to distinguish or to cater the interference component, the new parameter signal to interference plus noise ratio is taken care, and it is assumed to be more representative in case of the 5G signals. But the problem is that the problem with the SRINR was that it does not have any traceability when it was defined about 10 years back. So they have started to develop the SNRI parameter, and then they look for the traceability. So how INR is affected? So for this in figure, you can see there is a two possibility. We are having the two different tower. This is representing only the massive MIMO system. So each mobile is sending some signal to the massive MIMO base station. So it is also possible if any of the user which is stationed between the two different massive MIMO system, it may also able to send some signal to the undesired or the undirected or unrequired massive base station. So this is one of the station which is sending the additional signal to this. So normally this particular MIMO system is expecting signal from these three devices, which is known as the, technically it is known as CSI, okay, channel state information. But if this is also giving the channel state information to the MIMO system, which is not connected with this user, it may also receive additional. So it is desiring this as a desired signal, this part signal, but this undesired signal is acting like an interference to the operation of the massive MIMO system, which is this one. Okay. So at the same time, when the signal is being transmitted back to the user element, okay, so for each user, the MIMO is able to change the direction of a beam as per the location of the user. At the same time, there's a possibility the solid line is coming from the main intended user, while the dashed line is representing the signals coming from the massive MIMO system, which is actually meant to send the second user. So the dotted signal is representing the interference to the first mobile system. So this is known as the inter-user interference. It is also possible the other cell tower is sending some signal which is known as the inter-cell interference to the all mobiles, to the cells which is allocated to different base station. So there is a two possibility. The one dotted line is coming from the same base station or the MIMO system, whereas additional signal is coming from different cell or the mobile system. So there are two kind of signals which are undesired to the user. So these two signals which are not desired is termed as the interference. So from within a cell is known as the inter-user interference. The amount of a signal is coming from a different mobile tower or signal is named as inter-cell interference. So these two interference terminology are added while defining the value of SINR. Okay, so they are looking for CQI, that is channel quality indicator. So channel quality indicator is supplied by the mobile tower, but in the reverse case, all mobiles are giving the information about the channel state to the massive device. So this is the reason why we need to define another parameter as INR, which also taking care of the interference. So they so under the project the first study was made, comparison of the SNIR, EVM for OFDM and the BFB-MC signals. So two different signals along with the modulation techniques are generated. Okay, like you can see LTE1 and LTE2. So one is the desired signal, another is the interference signal, and this is also having one block like gain. Both signals are added, and the noise density is measured on a software named as a Keysight system view. After the measuring the noise density, when the value of SNR is changed from 30 dB to 90 dB, they have measured the value of signal to interference plus noise ratio in dB by increasing the value of interference gain. So gain is controlled by this block. So as the gain is increased from 10 to the power minus 4 to 10 to the power minus 3, there is a decline in the value of SINR. That means signal quality is reducing. And after having a value about 10 to the power, let's say minus 1, the signal to noise ratio becomes less than 10 dB. So here the value of interference as well as the noise has become prominent. So this particular variation is only effective till we are having a limited or low value of the interference gain. If the interference gain is very high, all values of SNR is taken or giving the same value of SINR. So this is the first study they have made to check the performance of the SINR with interference gain. They also check the value of SINR with respect to BER while changing the value of SNR from minus 5 dB to 20 dB. So for 5 dB, 0 dB, 10 dB, the values of the SNR, SINR are decreasing very slowly, and so the value of bit error rate is also reduced. For bit error rate is suddenly reduced when the value of SNRIR increase from 5 to 20 dB for the SNR value of 20 dB. So SINR is proportional to SNR as per this data. And second study was made to find out the relationship between SINR and the EVM. So with increase in the SINR, it was noted that the value of EVM is also decreasing. So EVM and the SINR are having the inverse proportional relationship. So with this graph, the new relationship between EVM in terms of SNIR has been generated. We can also reverse this equation mathematically, and so we can define SINR P dB equal to 20 log base 10 A by EVM in percentage. Okay. So if the value of EVM is known, we can able to calculate or estimate the value of SINR. So this is the contribution which they have made. One more measurement they have done, that for the same signal, if we do the measurement multiple times, so 2 time measurement, 5 times measurement, 10 times measurement, 20 times measurement, 20 times measurement. So they are sure there is a very small variation in the value of EVM if the more measurements are done. Okay, so you can see the variation in the EVM with respect to the change in the value of SNR is very little when the iteration is taken as a 20 iterations or the 100 iteration. They also predicted the error between the SNRIR, which is generated from the system for different value of SNRIR. So for 2, 5, 10, 20, 100 iterations, they have checked is there is variation. So you can, if you little bit focus this one, this is light green color 100 iteration, and this is the variation is here almost very small. While for the 20 iteration, this is little larger, but better than the error in case of 2, 5, and 10. So based on this stability of for the 20 iteration, it was decided that 20 iterations are chosen based upon this criteria, which will lead to the reliable reporting of the CQI. So we can come to this point that the mobile user can give their information to the radio stations or the mobile tower while the iteration is taken at least 20 or more than 20, then only the value of channel quality indicator sent by the mobile to the mobile tower is reliable or significant. In the second setup, they evaluated the value of SNRIR in a frequency selective channels for a massive MIMO scenario. Massive MIMO means more number of antennas, large number of antenna size. So they started with the design at 2.4 gigahertz. A small single antenna is designed. This is the design of antenna, and the directivity of this antenna is set at 3 dB, 3 dBi, 3 dBi, and this is the angular antenna. This is the angular antenna, and one more antenna they have designed, which is consisting the 4-port 1, 2, 3, and 4. So this is known as a 4-element antenna. So more element of antenna is giving the polarization diversity gain. So this antenna is implemented in a measurement setup, which consists of a building. A distance from a building is here. Okay, so here is a placement of the 32 element transmitter antenna, and this side the placement of the special receiver 1 to 4 antenna. So you can see here 1 to 4 antennas are fixed, and there is a distance between the element array or the receiver antenna. So this is the transmitter antenna array, which is consisting 32 element, and this is the receiver antenna array, which is consisting 1 to 4. This measurement is done at the University of Surrey in United Kingdom. After the measurement, they obtain the value of SINR by substituting these values, where the value of E is representing the OFDM signal, gamma square is representing the Gaussian additive noise variance, and these two are representing the pre-coded channels transmitting independent of OFDM signal. So these two is representing the interference signal, this is the desired signal, and this is the noise of the system as form of the Gaussian additive noise. So when they have checked the SINR value, which is measured data, and this is the SINR value, which is predicted data. So these two graphs looks to be same, but this is coming from the measurement and this is coming from the prediction of the SNRIR. The difference of these two is checked, and it is coming around 0.5 to +5. Okay, so there are one or two locations of a time or the frequency point where the difference between these two SNRI value is higher than -1 or +1. Otherwise, in most of the, you can say more than 95% of the frequency point or time, the prediction error is less than ±0.5%. So this measurement was performed. Now, to establish the traceability of SNRIR or the rated parameter, it is important that how the SINR is defined, and for defining these, what parameters are required, or whether these parameter which is defining the SINR are already having the traceability. So like we mentioned, the SINR is defined on the basis of power measurement, and RF power measurement is having or already is having the traceability established in most of the NMI. And the second thing is that what is the scenario in which the SINR data or the parameter is being measured. So whether we are talking about the measurement, SINR measurement in the direct connecting devices or through the air, over the air. So for the directly connected devices, we can use the oscilloscope like shown in this figure. Okay, like shown in this figure, we can use the oscilloscope, or we can use the vector signal analyzer when we are looking to measure for a over the air system. So there is some limitation with the digital real-time oscilloscope. This is limited by the sensitivity. Okay, it cannot measure the very less power. So like it is having the peak signal level of -20 dBm or higher, and it cannot measure 5 milliwatt per division less power. The second thing is that the second instrument is vector signal analyzer, and it is used to measure a peak signal of -50 dBm. So it can easily measure a signal which is very small, -50 dBm, and this should be compared with a typical set of a UE user equipment -70 dBm, or a value of the pass fail, let's say -90 dBm. So this vector signal analyzer can able to analyze the signal less than minus 50 dBm with sufficient. So they have made one oscilloscope based measurement in which this yellow covered part is performed in a software, and this is the measurement they have added on the addition. In the measurement also, sorry, in the software also, they have evaluated the value of EVM, as we have discussed the performance of EVM measurement here. Okay, so this is the EVM power measurement they have performed, and so this is the EVM data which is coming from the simulation, and the signal which is coming out from the noise density after combining the signal from FC1 and FC2 frequency, it is given to some RF generator. It is demodulated in form of the symbol sync real-time oscilloscope and given back to the IQ demodulation. IQ demodulation is separating the incoming signal into the I data, into in-phase data, and the Q data. This is again combined, and the value of error vector magnitude has been captured. Now the value of EVM, which is coming from the simulation and which is coming from the measurement or oscilloscope. Okay, this is the oscilloscope. Oscilloscope has been taken care and compared. So oscilloscope traces were measured over a 40 millisecond time approach corresponding to approximately 30 frames at 1.25 giga samples per second in a bandwidth of 2.5 gigahertz under sample. So these two EVMs are compared, and it is a performance. Second measurement was done with the help of phone tester and the EVM measurement. For phone tester, the radio communication analyzer is used. This is the from the NSO company, and this instrument is a platform that is able to perform both transmitter receiver characteristics measurement of the radio terminals in a mobile communication system. Okay, and the another signal generator which is combined with a modulation or the modulation assist technique WCDMA source and followed by the 6 dB amplifier or the attenuator. So this particular signal is acting like a interfering signal. So these two signals are combined with the help of 3 dB 90-degree hybrid coupler given to one of the user equipment Telstra 4G USB modem, and the signal which is being given to the UE is monitored with the help of Keysight PXA signal analyzer. So what is this? This is the desired signal or the wanted signal which is wanted to transmit, and this is a signal which is generated to interfere the signal. These two signals are combined with the help of coupler. One set of the input is given to the UE, and the second set of the input is given to the Keysight signal generator. Once it is checking on the performance, the signal generator, one can able to realize that how the incoming signal is changing or is deviating from the desired response. So measure, this is the representing the measured results for a adjacent channel interference, and this is the view from the signal analyzer. So finally they are able to evaluate two parameters, EVM and CQI, with respect to the value of interference power. So on changing the range from minus 50 to 20 dB, CQI value changes from, let's say, minus 15 to about 7. Okay, while the EVM parameter has increased from, let's say, 2 to about 25. So this is the increase of the this is the enhancement of the EVM signal with the increasing the interference power, EDBM. The test measurement compare the CQI reported for the downlink to the UE together with the measured EVM. One more study made by the M. Wong, rigorous link performance and measurement uncertainty estimation for the MIMO OTA. So these are some equations to define the SINR and the EVM, and it can also be normalized. So these two equations are defining the SINR and the EVM. We are skipping a little bit. And the SNRI, as we discussed in a previous example, is affected by the two kind of interference. One is from the same system, the second one is from the other system. So mathematically, they have incorporated the interference from the same system as well as from the different system into the measurement with the help of this equation. With the help of this equation, and finally they evaluated the value of EVM and the SINR. So these are the equations which is taking care the interference from the different systems. So this is showing that f the x1 x2 is coming is the two adjacent symbols sent from the two different antennas. So this is a simple equations obtained on the receiver end, which is a function of these channels H11, HI1, H1J, HII, because this is representing the transmitter side, this is representing the receiver side. So y is a function of the H n, and the noise is introduced in the receiver side. So once the noise is introduced, the equation becomes the function of y is a function of h1, this h coefficient, x values, and the n. So mathematically or in matrix form, we can write h in bracket x1, x2 plus n. When we are introducing the interference signal, let's say in, this will have addition here, and we can write the value of, we will have a new value of y as a y prime f1, y prime star f2. Okay, so this consists of the the h coefficient, x data, I data, and the n data. So this is the contribution done on the receiver end from the different systems. So for checking this performance, they have made a measurement setup at LTE band with the help of single input, single output test bed setup. This setup is made in an anechoic chamber, and in the anechoic chamber they have using one horn antenna to transmit the signal and one 45-degree slant MIMO antenna. So this MIMO antenna is the similar antenna which we have discussed earlier. So this antenna is like, this is the MIMO antenna, 4-element MIMO antenna, 1, 2, 3, 4. So this is only the representation of the MIMO antenna, 45-degree slant MIMO antenna. So this setup is made, and there are some measurement technique. A 45-degree slant MIMO antenna is employed at the UE, and an ETS Lindgren 3117 double rich horn antenna is employed at the BSC. So this is the horn antenna, and this is the MIMO antenna. So they are employed, and signal power from the signal generator is changed, and it is received on the other end. So when the value of input power is changed, there is a change in the value of EVM also. So as soon as the power level of the input signal is increased, there is an increase in the value of EVM. They also estimated the value of uncertainty associated with the measurement of EVM. So this bar is representing the value of uncertainty in the EVM. So we can see as the value of RF power is increasing, the value of uncertainty associated with the EVM is also increased. So this can be judged by the higher value of bar for the EVM measurement. So for example, -10, we are having a small size of a bar. For 0 dBm, we are having the large size of the bar. So the uncertainty with the EVM measurement is also increased with the increase in the power level of the signal. In the second setup, they have used the two antenna. Okay, so this setup is only for a single horn antenna usage. This setup is with the help of two antennas. So at the same time, it can able to transmit the two signals. Again, the two signals should be very different. So we are having the VP, vertical polarization signal, and HP, pointer polarization signal. So these two signals are sent and captured with a UE extra 45-degree slant MIMO antenna. Okay, so whatever power is received, that is captured with the user equipment, and at one time additional signal is generating by the new function generator or the vector signal generator as a interface. So already the link is established between this transmitting antenna and the receiving antenna communication between these two is making disrupt by adding or generating a signal from the other horn antenna. So this is acting like a interface here. So in this scenario, the measurement of the SNR is taken as a measurement of SINR. In a second setup, the different frequency is generating and the value of receive and the beam antenna is sending some signal. Beam antenna is sending some signal. It is captured by the VP and HP polarized horn antennas, and the signal captured is now checked on the spectrum analyzer. In this moment also, the interface is generated by the third vector signal generator. So this is a downlink communication. Okay, this time the signal is coming from this direction. We are generating an interface on this, and in the swept downlink SINR measurement, the signal is generating from the user equipment going in the direction captured by the horn antenna, and then again it is generating one interference signal. So that is the difference between the uplink and downlink performance. To check the uncertainty value of the channel power measurement, a equation is proposed, which is a function of 2 sigma mu, u frequency response, uncertainty from the input attenuator, uncertainty from the absolute measurement, uncertainty from the resolution bandwidth, and uncertainty from the mixer input. So these values are taken for all these parameters, whereas sigma and mu are representing the repeatability, standard deviation, and mu is the average value. Okay. So on getting this value, the value of uncertainty is estimated, that is termed as a general power measurement relative uncertainty. So this bar is representing, in this graph is representing the value of uncertainty associated with the each measurement. So we have discussed about the downlink measurement and the uplink. So we have discussed about the uplink measurement, how the uplink measurement is performed, how the downlink measurement is performed. In both scenarios, the value of SINR is estimated, is taken, and the value of uncertainty is estimated using this equation. And on substituting this, you can see there is no change in the value of uncertainty value, while we are changing the corrected power level from, let's say, minus 45 dBm to minus 20 dBm. So there is a change of the power from minus 45 dBm to minus 20 dBm, and the value of the bar, as you can see here, all are giving you the same values of the same data, is same, but the value of uncertainty in the measured DL channel power is increased. Okay, and this is representing uncertainty of the measured UL channel power. So downlink power is increased as we increase the value of downlink signal. If we see the traceable DL SNR data with respect to power level of the BSC RF port setup, so this BSC is this one, base station emulator. So by changing the power level of base BSC RF port setup minus 45 to minus 10, the value of the DL SINR in dB is increased for the condition of the Gaussian noise minus 40 dBm and the noise floor of minus 93 dBm. This is the response for the uplink EVM measurement, which shows the increase in the value of EVM with the higher value of SINR. This is the downlink throughput measurement. How much signal is captured in case of the downlink measurement? That there is a certain value below which there is no increase in the value of SINR. Only after having the value of SNRI greater than 1, we can get the DL throughput. That means if the value of SNRIR is less than 0, there is no signal which is being transmitted. No signal is transmitted in the downlink downlink transmission. They also studied the 5G test bed method, where they have designed the system like this at 26 gigahertz and with 20 megahertz bandwidth. So this is a transmit system consisting of detector, mixer, amplifiers, isolator, and the antennas at 26 gigahertz. And on the receiver side, they're using the 6 dB pad mixer, a power divider, and doubler power supply and LO source. The signals coming from two output in phase as well as in out of phase is captured as channel 1 and channel 2 in a vector signal receiver on the receiver system. So this setup is working at 26 gigahertz. After the setup, they have performed the measurement, and this measurement they have compared the value of desired SINR dB with value of the measured SINR dB. So which they have found a linear relationship. So there is a small deviation from the starting value. Otherwise, the value is almost linear. So the measurement is performed on the two system, one with the help of traceable PSA measurement, spectrum analyzer measurement, and the second one is the vector signal analyzer measurement. So these two data are compared, and you can see almost same data is or same difference is obtained between the measured SINR and the desired SNR. Although there is a change in the value of or difference in the value of these two measurements at higher range greater than 20 dB of the desired SINR. This also represent the under figure represent the value of AVM for the downlink and the downlink SINR. That means the relationship between the SDVM and the SINR, which is again inversely proportional to each other, and irrespective of the modulation QPSK 16 QPSK 64 QM or the 256 gram, the relationship between the EVM and the SNRI does not change. See, since it is showing as a single line. The same is applicable here between the downlink EVM and the downlink SNR for the subframes. So we are taking one single modulation technique, a single modulation method, 16 QM, but the number of interferences increased 1, 2, 3. But there is a small change in the value of EVM and the downlink SNR. So again, for the SNR higher than 20 dB, there is we can distinguish the value of 16 QM and the 16 QM with the 3 interference. So similar measurements are performed again for the downlink EVM, downlink between overall downlink EVM and the downlink SINR for different modulation techniques, and they have checked that by different modulation techniques for all subframes, the values are slightly changed or different, but all are following the same pattern. This is the value of the normalized overall downlink EVM that is almost having the same performance. Another group led by Humphreys made millimeter wave testbed, and this testbed is containing number of equipment like it is placed here: digital to analog converter, analog to digital converter. This is transmitter local oscillator frequency. This is receiver local oscillator, and this is showing the eight transmitting channels. And between these two, open over the air channel is formed. Okay, so this is made to operate between 28 to 31 gigahertz. It supports up to 18 channels, and it is fully, and the RF front end is fully independent of the software and baseband hardware. So we can able to add any, or this can be operated to any other frequency range also. So this is the communication channel they have made to operate in this millimeter wave, and on generating the internet interface, like the increasing the value of interfere power, the value of SINR is getting reduced. So initially, for a very low amount of the interfere power minus 40, the value of SINR is about 28, whereas as the value of this is increased to, let's say, suppose 5 minus 5 dB, the value of SNRI reduces to about 10 dB. So the value of SNRIR is inversely proportional to the power of interfere. This is also giving the channel information by the internal interference. So for different conditions, the values has been obtained, which is forming the channel state information sent to the mobile tower from the mobile. They also estimated the channel symbol rate for the in-phase case and the external case. So both the cases, the symbol error rate is obtained with respect to the value of SINR. So with increasing the value of SINR, the error rate is reducing. So this error rate is similar to the bit error rate which we have defined, BER. So by performing all these study, the new definition for the SINR is defined for the application of 5G devices or the network. In defining the SINR, the three different committees were discussed. Third generation partnership project committee, which is having a separate committee to define the definition for SINR, known as a 5G Innovation Center at the University of Surrey, number one. Number two is the European Telecommunication Standard Institute that established a new group, Industry Specification Group. The second is made between the University of Surrey and the NPL UK. So these three different groups have combined together and they have given the new definition for the SINR. While defining the new definition for the SINR parameter, which will be implemented for the 5G devices or the network, the few factors are considered. The first thing is that we must use the term interference, which is in form of the additive white Gaussian noise. And the second one is that it should be applicable to narrow band as well as the brushy signal that can be come anytime in the range of 5G frequency range. As well as we also consider the signal in a 5G network is being communicated with the help of more number of antennas, that is the MIMO and the other complex systems. So this part also be covered in the definition of the SINR. So there are two possibilities: either there is a single input, single output kind of a system, or multiple input and multiple output system. So for both the system, there is a difference between defining the value of SINR. So the definition one, which is taking care of the adjacent carrier. Okay, so we wanted to transmit the 5G waveform, but at the same time, the nearby frequency is sending the IoT data or the IoT communication, as well as 4G OFDM is also sending.
In 5 minutes, I will see you.
So there's a possibility that 5G waveform get interfere from the 4G waveform as well as from the IoT narrowband. So the definition of the SINR should take care of the interference from these two signals. Second point for the definition of the SINR is for the small cell SS. Okay, so normally we can have the receiver terminal antenna, and this is the transmitter end of desired signal, and this is the desired path. But there is a possibility, since the distance between the second interference signal and the terminal antenna may be small, and due to the scattering by any object, the undesired or the interface signal may reach to the terminal antenna. So here also we need to define a different value for a SINR. So this definition is aimed at millimeter wave high frequency, more than 24 gigahertz, to cover both immediate and the long-term uses of the future generation communication network. For example, 24 gigahertz, where the interference scenario is also understudied. Okay, it's not properly defined yet, but it is under it is undergoing. Okay, third definition is taking care of the massive MIMO system, where we are assuming the interference signal is coming at the null point of the radiation. So this point is representing null point where the amplitude of the transmitting signal is very small. So if any signal which is coming in this null point region, there will be no reception from the massive MIMO. But if the beam is little bit changed from the previous direction, there is a possibility that interfere may insert and captured by the massive MIMO system. So here SINR value can be maximized by suppressing the value of interferer, or in opposite case, the SINR is reduced due to the interference from the delayed update of the channel state information. So if the user is not updating its location or its position to the mobile tower, there's a possibility the value of SINR may get reduced due to the presence of interference. So it is also required that channel state information must be updated very soon or very quickly to maintain the communication above the SINR threshold for all users. So there is a summary of all these measurements that performed under the Euromet project. They have defined the new definitions for the SINR. They have established few measurement techniques. They also established the traceability of the SINR. So three major contributions which is made by this project. Okay, so another report which is given by Dr. Brown, and he has given the new values or the new equations for the signal to interface ratio SIR, and I'll just giving this is the mathematical part. He also studied the performance of SIR for the 4x4 MIMO channel at 5 gigahertz measurement. Okay, so after performing this project from the Euromet or from the European country, let's look what the NIST has performed in the contribution for the 5G metrology. So they started a project named 5G 6G core networks and services, which is aiming to develop the conscious standards and the best practices for the evolution from 5G to 6G. And they have focused on the core network and end-to-end network services. So they have decided total 5 tasks. One of the important tasks was to develop the metrology for the 6G core networks and the services. So developing measurement methods, models, and tools to fit the measurement gaps in 5G and 6G schemes. And they are having some focused objective, measuring the AI-based 6G and E2E, end-to-end network services. So that was their aim, and it is still outgoing since it is started in 2022. So there are some requirement from the NIST side for establishing the metrology for 5G and beyond. So there are more number of systems which is coming to operate at 5G bands, as well as there are new measurement requirement, especially for the traceable radiated channels over the air test method deployment. They also need to characterize the new radiation path if the number of users are very much more or very much high, or if the users are very close to cover or to operating at a millimeter wave frequencies. Okay, they also take care of the active multi-beam antennas and the MIMO systems. Also, they also taking care of the massive MIMO antenna array, which is containing or changing the beam. They're changing their beam with the help of involving integrated electronics and digitally synthesized signal generators. Okay, so to address these kind of uncertainty issues, also NIST has developed a software tool, the NIST microwave uncertainty framework, that allows to build uncertainty models of instruments and systems, track correlations, and use Monte Carlo simulations to help estimate to help estimating the uncertainty. So they also take care of the same kind of parameter, bit error rate, EVM, and the RMS delay speed while deciding the metrology for 5G network. So first technique they have established, that is calibrated millimeter wave monitored signal cabled source to receiver, and this is established in a frequency range of 70 gigahertz. Okay, and there are a number of errors which is contributing into the signal quality, like the frequency response, impedance effect, interleave errors, and other nonlinear effect. Extending this characterization to the millimeter wave band will also provide improved channel sounding and the calibrated electromagnetic environment sensing and simulations. So this kind of a setup can be extended for frequencies higher than 70 gigahertz. They have not actually discussed the simulation or the measured result of this data, but they have established the same techniques. Okay, similarly, if we are having the signal which is captured with the help of antenna, which is acting like a radiated source, and how the receiver is measuring. So this particular figure, this particular area is representing the antenna. They have developed this antenna is receiving some signal, and this signal is being captured over here system. So the captured signal by this antenna can be observed on the display of this analyzer, and the field strength can be measured in a far field as well as in the quasi far field region. So various antennas can be changed from the millimeter wave as well as covering various frequency ranges, and the value of field strength can be measured. So this is again could be made as a traceable. Okay, they also establish the reverberation chamber to check the performance of the modulated signal. So we have earlier discussed about the OFDM signal and the quadrature amplitude modulation signal. So if any 5G signal is coming with the modulation, the effect or the impact of the modulation, the characteristics of the modulation can be captured or measured with the help of inside a reverberation chamber. So you can see here, this is a box. This is a box, and this window is you can able to see how this antenna is placed inside this chamber. So this is the reverberation chamber. To measure the multiple signal together at the same time simultaneously, there is a possibility that one set of the terminals can be act as transmitter, whereas the other side of the terminals can be act as a receiver. Okay, so we can simultaneously, if we are having the multi-port device like this is shown here, we can able to send a more number of transmitting antennas or signals at the same time. We should able to receive, we can able to receive the same number of channels. So for such kind of a metrology, the two information, what is the angle of departure and what is the angle of arrival, is the important parameter for such metrology. So this is the 16 element receive array which is made by NIST mmWave mmWave group, and this is operating at 83 gigahertz. So this one is operating at 83 gigahertz, and this is operating at a 60 gigahertz. So they have made the channel sounder operating at these two frequencies. Okay, and the location of this channel can be replaced. So in this figure you can see channel sounder is placed on the robot, and depending on the location, so this is the receiver and this is the transmitter tripod. This can be locate its position from here to there, and the effect of the received signal is measured on the receiver side. So they have made one intentionally robot and one 16 element receive array is placed over there. By changing the location of this, the change in the signal strength has been measured. And finally, the NIST also proposes the antenna metrology for smart antennas and the MIMO system. Since we wanted to characterize the MIMO antenna simultaneously which can be deployed for the 5G mobile tower. So for this, they have made very big, large antenna positioning system, and this is containing the two robots. The robot one is stationary. Okay, so this is having a fixed position. This is giving one beam, and the second one antenna is placed on a linear rail. Okay, so this can change its position from here to there, or left, right, or up and down, and the beam is steering from here to there. So we can able to control the value of, we can able to control the direction of a beam from this direction to the other direction, depending on the position of the antenna. So this is made, this antenna is fixed, this antenna is variable. Wherever there is a change in the location of the receiver, this antenna, the beam can be steered in that way. So that is the measurement performed by the NIST scientist. So that the system, they develop a system, and in short it is named as a labs. So this is the figure of the lab system, and you can see this is a very big system containing anechoic chamber along with the robot and the absorbers. So this labs consists of 6 degree of freedom articulates arm robots. That means it can move to 6 different directions, left, right, up and down, and in a diagonal dimension also. And one is fixed. So let's say this is fixed, and one is at a 8-meter long floor mounted rail. So another is mounted on a rail, as we have seen in the previous slide. It can track and measure multiple beams from electrically steered array antennas and simulate Doppler effects using dynamic antenna position. So this is a system which is designed to work in some higher frequency range, and let's say this is a range of 70 to 75 gigahertz. They're also establishing two antenna positioning system, which will be covering in the range of 1 gigahertz to 500 gigahertz. And unfortunately, they have not shared any kind of results from these antenna setup or the metrology for the 5G. So I just discuss the setup which they have established for the 5G signal analysis. So the major contribution which they have shared on the internet is NIST MUF, okay, measurement uncertainty framework. So this is a tool which allows to assign the uncertainty, and this is a snapshots from the software. From here we can able to choose depending on our uncertainty analysis of any measurement. On this side, they're also giving a range of the parameter which can be used for selecting a certain measurement setup. So overall, we can conclude about the SINR measurement and its requirement for a metrology. So SINR, as studied by the various NMI metrologists, it is an important parameter for the performance or for the study of the 5G communication channel. Any product which is being developed for establishing the 5G communication network, SINR has to be measured. For uplink and downlink measurement, there are 2 different set of measurement depending on the frequency as well as the test setup. Factors which can influence the SINR in the 5G new radio are: what is the distance of the user equipment from the base station. As the signal strength decreases with distance, which will lead to the reduced value of SINR. Interference, how other equipment users or different cell towers are placed near to the user device. The noise, most of the time it is coming external noise, like additional sound is coming, additional devices under operational. What is the atmospheric condition, if there is any lightning or the device which are operating are not radiating any additional signal. The last one is the multipath effect. Okay, the signal is coming directly or it is coming through the scattering. So these all four factors are affecting very much to the value of SINR. So based on the value of SINR, the base station will decide about the selection of modulation as well as which kind of a coding is required to be sent to the user equipment. They also decide the kind of wave forming and the MIMO technique which is being placed with that for controlling the value of MIMO operation. The next thing is what is the resource scheduling, because most of the time the user equipment, like we are talking the mobile phone, it's not sure that if we are talking mobile phone at one location, maybe in the next 5 minutes we may be able to change our location from the previous location. So the location as well as the position of the user equipment must be continuously known to the base station or the mobile tower, so that it can reschedule the CQ data or the CSI information. So this is the application of the SINR data or the measured SNIR data. So as suggested, the network operator can able to use some techniques to enhance the value of SINR by optimizing the placement and orientation of the antennas to achieve better line of sight conditions and reduce signal obstructions. They can also reduce interference from other devices by changing frequency or channels. Can also able to improve the SINR. Network operators can use advanced technologies, beamforming and MIMO systems. And the last one, using high quality equipment and increasing the transmit power of the signal can also be enhanced SINR. So these all are the some techniques which is taken care by the network operator. Like we are having the Jio, Airtel in India, and there are various companies which are also developing the product of the 5G. So in overall discussion, or I would like to conclude that SINR is a very important parameter for establishing the wireless communication channels or systems operating at a 5G band. Number one, there are test methods are available, which are providing traceability to SINR. In future, the value of SINR are under studied to operate for the millimeter wave communications more than 24 gigahertz and so. And most of the reported data are limited in a frequency range or limited in a frequency band. We need to have a proper SINR measurement setup at national level, which can easily carry the traceability from the NMI of the India. So with this, I would like to conclude my talk, and this is my team member. We are working on the various 5G and the 5G systems, starting from antenna to some system. Thank you very much.
Thank you very much, sir, for this wonderful presentation. Would you like to add something? Sir, kindly unshare this. Thank you very much, sir. So it was very important topic. With your kind permission, I would like to share your presentation with all the participants and on our government website of the legal metrology, as well as on our social media platforms, your video and your presentation, if you kindly agree.
Sure. No problem.
So kindly share me your presentation immediately after this, and we will share it. Thank you very much, sir, for this brief and wonderful presentation. I would like to thank all the participants. We will meet with the next topic next week. Thank you very much. Thank you all.
Thank you.
Thank you. Atulji, photographs. You are taking the photographs?
Okay, sir.
Thank you.
Thank you.
Thank you very much. Thank you. Thank you.